Hello. This brief video is intended to introduce the empirical rule, which is a way of examining the normal distribution. The normal curve shows up a lot in statistics, and consequently a lot of statistics involve the normal curve in some way. Now that said, there are a lot of cases where the normal curve is actually not appropriate. For example, if you're looking at Likert scale data, which is an ordinal scale, or if you're looking at logistic regression, these types of data or processes actually don't involve normal data, and what we're talking about here wouldn't apply. But in a lot of other cases, the normal distribution is quite useful. Much is known about the normal distribution. It has a bell shape, which means it's symmetric about the mean, and the spread is determined by the standard deviation, or more specifically the variance, which is the square of the standard deviation. And as a consequence, we can determine how much of a population should be if that population follows a normal distribution. Standardized scores, or z-scores, take advantage of the normal distribution. The normal distribution is symmetric about the mean, and the standard deviation measures the spread of the values away from that mean. In particular, it's actually the inflection point where the bell-shaped curve goes from having an upside-down bowl shape to what would be considered more of an upright bowl shape. The standardized score essentially is asking how far a value is away from the mean, be it above or below the mean, in the number of standard deviations. So we can think of the standard deviation being used as the unit, and with that unit we could actually imagine creating a ruler where we ask how far our value is above or below the mean. In this case, I've marked out the standard deviations based on whole standard deviations and 1/3 of the standard deviation. The standard empirical rule, which is often called the 68, 95, 99.7 rule, indicates that about 68% of the values fall within one standard deviation of the mean. That means starting at the mean and moving up, or starting at the mean and moving down, you'll capture about 68% of the data. Consequently, if you were to move out 2 standard deviations above or below the mean, you would capture about 95% of the entire data. And going yet one more standard deviation, 3 standard deviations above or below, you would capture 99.7% of the data. Let's look at this with a contextualizing example. The number of blue-eyed drivers registering each week for licenses at a particular driving license office seems to follow normal distribution based on previous data. They also know that the mean number is about 80 drivers per week, and the standard deviation is 15 drivers per week. So the first thing we'll do is we'll sketch the curve and mark off the values that are important for us. We know the average is 80, and if we add 15 to this, we get 95. Add 15 again, we get 110, and add another 15, we get 125, where we added 15 each time because that was the standard deviation. Going in the other direction, we subtract 15 and we get 65, subtract 15 again and we get 50, subtract 15 and we get 35. So 3 standard deviations below would be 35, and 2 standard deviations below would be 110. Now again, this follows the empirical rule, so we know how many of the values fall within these intervals, roughly speaking. So for example, 68% of the time, we would expect to see the values between 65 and 95. The middle 68% of weeks will have how many blue-eyed drivers? Again, as I just said, it would be between 65 and 95, 1 standard deviation above and below. What is the percentage of blue-eyed drivers numbering between 35 and 125? Well, if we look at the curve, we notice that 35 is 3 standard deviations below the mean, 125 is 3 standard deviations above the mean, so that captures 99.7% of the population. Or said another way, 99.7% of the time, each week will contain between 35 and 125 blue-eyed drivers. 2.5% of the time, there will be this many or fewer blue-eyed drivers. Well, to understand this one, we need to recognize that 2.5% is the value outside of the interval. And we notice that the interval from 50 to 110, which is 2 standard deviations above or below the mean, captures 95% of the data. That means that there's 5% of the data not in this interval. Because the curve is symmetric, half of that 5% is below and half of that 5% is above. So 2.5% of the time, there will be 50 or fewer drivers per week. Now, there's an alternate empirical rule that I prefer, and I refer to it as counting by the off thirds. And this takes advantage of the fact that if we're counting by thirds, we get nice percentages, whereas the 68, 95, 99.7% has nice cutoff points, namely 1, 2, and 3 standard deviations. It doesn't have the nicest of percentage points. 68 and 99.7 aren't common percentages that we use. The alternate empirical rule, within 2/3 of a standard deviation above or below the mean, we capture 50% of the data. Within 4/3 of the standard deviation of the mean, we capture 80% of the data. Within 5/3, we capture 90% of the data. And then finally, within 7/3, we capture 98% of the data. Now, most people would agree that 50, 80, and 90 are relatively reasonable percentages. Some people at first balk at the idea that 98% is a nice percentage. Well, if we think about it this way, the 98% captures the middlemost 98%, which means that there's 2% above and below. But if those are divided in half to recognize that there's 1% above or 1% below, most people see the value of having the upper or lower 1%. Continuing with our previous example for blue-eyed drivers registering per week, we start with the average, which is at 80%. And I noticed that the tick marks below count off by third standard deviations. If the standard deviation is 15, a third of that would be 5. So I can count off by every 5 to see where my values would land. So from 80, 85, 90 would be 2/3 of a standard deviation. 95, 100 would be 4/3 of a standard deviation. 105 would be 5/3 of a standard deviation. 110 and 115 would take me to 7/3 of a standard deviation. Going in the other direction, we would have 70, 60, 55, and 45. Again, 60 is 4/3 of a standard deviation below 80. 4/3 of 15 would be 4 times 5, which is 20, and we see that 60 is 20 drivers below 80. What percentage of weeks we'll have between 80 and 100 blue-eyed drivers? Well, we recognize that between 60 and 100 captures 80% of the data. Since the curve is symmetric, half of 80 is 40, and that would be between 60 and 80, and the other 40 would be between 80 and 100. So there would be 40% of the weeks in which you would have between 80 and 100 blue-eyed drivers. Now the shapes can be even more complicated. What percentage of weeks we'll have between 70 and 105 blue-eyed drivers? We notice that this is not a symmetric curve about the mean. But we know that between 70 and 90, there are 50% of the drivers. Half of that value would be between 70 and 80. The other half would be between 80 and 90. So half of 50 is 25%. So 25% of the weeks will have drivers between 70 and 80 blue-eyed drivers. Alternatively, between 55 and 105, which is a total of 5/3 standard deviation, that captures 90% of the data. So 45%, or half of 90, would be between 80 and 105. So adding 25 to 45, we would see that about 70% of the weeks will have between 70 and 105 blue-eyed drivers. And as our last example, only 1% of the time there will be this many or more blue-eyed drivers. Well, again, we recall that 98% of the time, the number of drivers that are blue-eyed will fall between 45 and 115. If this contains the middlemost 98%, 1% would be below 45, and 1% would be at 115 or above. So there would be 115 or more blue-eyed drivers only 1% of the time. I hope this was helpful. Thanks for listening. Goodbye.